In this video, I'll be looking at rearranging equations, and I'll be looking to explain why rearranging works. At the core, what we're doing is we're looking at the operations that take place in an equation, and we're going to use the opposite operation to cancel out things on one side of the equation and take them over to the other side of the equation. The reason that it moves from one side to the other is because in order to keep the equation valid, we have to do the same thing to both sides of the equation, otherwise we change the nature of the equation. So, looking for these opposite operations. The first thing that we can use is that x, take away x, equals 0. So if we have something added or subtracted from one side, we can do the reverse operation. So plus is the opposite of minus, and minus is the opposite of plus. So if we have something added on one side, we take it away from that side. It becomes, those two terms then become 0 on that side of the equation. And on the other side, we have to be consistent, so we take it away from that side too. And vice versa, if we have something taken away on one side, we add it on, we must add it on to the other side. Next, we have x divided by x equals 0. So this is for multiplication and division. I think that's what I'm doing here. Yeah. If we have something that's multiplied on one side, we can use the opposite function here, division, and that will, not x divided by x equals 0, that equals 1. Right, so there's two things you have to understand about this. So x divided by x equals 1, and if we have something multiplied on one side of the equation, if we divide by it, then that term divided by the same term becomes 1. We then must do the same thing on the other side, so we've got to multiply or divide. But then the reason that this works is because 1 times x equals x. So we have now, if we had something multiplied by x on one side, and we divide by that x, then whatever that term is, it will be multiplied by 1, which is just equal to that term, whatever that term might be. So these two kind of work together here. And the other opposite function we're looking at is squaring, so x squared or x rooted here. They are the opposite functions. And here, x squared, square rooted, or x square rooted all squared, they're both equal to x. So we can use that to help us also. At the moment, what I'm talking about here is quite abstract. Let's do some examples so we can see how this plays out. We'll start off with a very simple one, f equals ma. And in this case, we want to calculate m. M is the unknown that we want to calculate. We know values of f being 800 newtons, and a is 5.0 meters per second squared. So what I want to do is isolate the mass term here, the m term. In order to do that, I need to find out a way to get the a to the other side of the equation without changing the nature of the equation. It needs to be the same equation. I'm just rearranging the variables and keeping the equation valid. So this means the same thing as m times a. So the operation here is a multiplication. The opposite of that is division. So what I will do is say f equals m times a and divide by a. In order to do that on this side, I need to do the same thing on this side. So I've got f divided by a. So that means I haven't changed the equation. I've used the opposite function. Now, a divided by a equals 1. So this cancels out. As a over a equals 1. And 1 times m equals m. So you see, the other thing is stays there. These two cancel out because they're 1, and 1 times m is equal to m, so I don't need to write the 1 there. That's why it disappears from that side of the equation. So now my equation is m equals f divided by a. Put the values in. It's 800 over 5.0, and that is 160 kilograms. So I've solved my problem. Rearrange the equation, put the values in, got my answer. Let's do another example. I'll clear the board for this one. Okay, this time we're going to use this equation, v equals u plus at. And I want to calculate a. A is my unknown. Okay, so I've got to find a way to get the a all by itself. Now what I need to do here is deal with any addition or subtraction before I move on to any multiplication. That's the thing you have to do. Because I have addition and I have multiplication here. This is the same as u plus a times t. Okay, and because I'm doing I want to get one of these multiplied terms by itself, I have to deal with the addition here first. Okay, you can also further understand that as plus u plus a times t, right? So imagine there's a plus there. Or you could say, to put it more straightforwardly, I suppose, a times t plus u, right? Now I want to get the u to the other side of the equation. So I look over here and x minus x equals 0, right? So if I write this as v minus u equals a times t minus plus u minus u. Okay, I'm writing this one straight away because I'm doing the same thing to both sides of the equation, right? Same thing to both sides of the equation. That's why I'm writing that one there. To both sides. Okay? So what I'm left with here is v minus u, and then I have a times t plus u minus u. These two here equal 0. So they cancel out of this side of the equation. So I have now v minus u equals a times t. I haven't finished my rearranging, I've got another step to do, and that is I need to take the t to the other side, to the left-hand side here. So let's do that. I've got a multiplication, so I need to do division here. So v minus u divided by t is equal to a times t divided by t. Just as before with f equals ma, these two cancel out here. So this is the same thing to both sides here, okay? And that equals 1. 1 times a is a. So that's my rearranged equation. a equals v minus u over t. And if I need the values, I can work out the value for that, which is, let's say it's 9.5 minus 0 over, I'll put that 2.8. So this is something that is accelerated from rest. So if it's from rest, then u is 0. This is a CVAP problem. It reaches 9.5 meters per second in 2.8 seconds. Anyway, the actual understanding of the equation is not too important. We're focusing on the rearranging, and that comes out as 4.1 meters per second squared. Okay, so another example there. Let's do one with another operation, which is a squared. So this equation, if I clear the board, is s equals ut plus half at squared. This is the equation I always use to explain why you can't rely on these triangles. Some people do. I don't know if I'm right. Which one is it? No, f equals a. Yeah. You can't put this into a triangle like that. So if you're still using those, you need to upgrade your thinking to proper rearranging. that's our equation, and we want to find T. I won't be harsh, we will take U to be 0. That has a nice simplification. S is 120, and A is 9.8 meters per second squared. So in this problem, this would be perhaps something being dropped. It's dropped from rest over with an acceleration of 9.8 meters per second squared, so that's free fall. If it was free falling for 120 meters, how long would it take to reach 120 meters? Right, so we need to get the T by itself. Now, sometimes you have this problem and you can't cancel out this term, but because the U is 0 here, that makes things a lot easier. So S equals UT plus half AT squared. I suppose you could say here as well that 0 times x equals 0, right? So if you know that, that's really useful. U is 0. So if U equals 0, then anything multiplied by U is still 0. Okay? So that whole term there drops out because U is 0, that equals 0 there. And therefore our equation becomes S equals a half AT squared. By getting rid of that term, it's going to make it so much easier rather than having to deal with these two instances of T here. Now we can continue using what we've seen so far. We want to get the T by itself, so we've only got multiplication and division here. This is the same thing as saying AT squared divided by 2. Okay? So we've got a division with this 2 here. The term that we're interested in, T, which is at the moment squared, but it's divided by 2, so we need to take the 2 to the other side. And also, going back to the correct order to do things, so you have to do addition, subtraction, then you have to do multiplication, division, and then you have to deal with powers and roots. So you see the T is squared here. Just the T is squared, nothing else is squared, so we have to deal with that last. That's why I'm dealing with the A and the 2. I'm going to deal with the 2. It's divided here, so I need to use the opposite operation, which is multiplication. So this is S times 2 equals AT squared. So I've divided by 2 times by 2. The 2's cancel out there. That's why it's gone to the other side of the equation. So I've got 2S equals AT squared. Now deal with the A. It's multiplied by T, so I need to divide it on both sides of the equation. So I have S, I'm going to write 2S rather than S times 2, just easier. Divided by A equals T squared. I should keep the A there, shouldn't I? Right, so I divided both sides, that's why I've divided on this side. And then, so T squared is equal to 2S over A. And I said that the root is the opposite of squaring, so T, right, what I need to do here is I need to square root the T squared and square root this side of the equation. This simplifies to just become the T, like this simplified just to become the X. So T now is equal to square root of 2S over A. And if we put the values in, 2 times 120, which is 240, divided by 9.8, all square rooted. When you put that into a calculator, you get 4.9. Round up to 2SF. So that one had the new function here, the squaring, and we dealt with that last year to do the opposite there, which is a square root. We'll do one more example with the ideal gas law, and I'll notice a few other things that you can do once you're actually substituting numbers in. Let's clear the board for that. Okay, so this is the ideal gas law. The pressure times the volume divided by the number of moles multiplied by the temperature, which has to be in kelvins. is constant, so the initial conditions all multiplied and divided like this will be equal to the final conditions multiplied and divided like this. We want to find P2. All of the variables are involved here. There's a change in pressure, there's a change in volume, there's a change in the number of moles, there's a change in the temperature. So each one of these, PV and T, they all change. That means we can't cancel anything out immediately. Okay? We have to rearrange the whole equation and then solve the problem. So we'll rearrange the equation and then see what the values are. So this is the variable here. That's the variable there that I need to calculate, and that means I need to take the N2, T2 and the V2 to the other side of the equation. Now when doing this, as you get used to rearranging, you'll look for steps that you can combine. So here I've got N2 times T2 on the bottom here, and neither of those are what I want to find. I want to find the P2. So these two terms here are collectively being divided by, or dividing the P2. So I can collectively multiply those as well. So what I mean is this. I write the equation out here. Equals P2 V2 over N2 T2. I'm going to multiply this side of the equation by N2 T2. Okay? And that will cancel out because just as N2 divided by N2 equals 1, well so does N2 T2 divided by N2 T2 equal 1. Both of those are true, so that enables me to take the N2 T2 to the other side of the equation straight away. So I've got to have times by N2 T2 here. And that's dealt with the whole bottom row all in one. If you're not comfortable doing that, that's totally fine. Just multiply by 1 each time. So you multiply by N2, that cancels out the N2, takes the N2 to the other side. Then multiply by the T2, takes the T2 to the other side. You can do it in individual steps until you get more comfortable with these rules. Okay, so now my equation is P1 V1 N2 T2 over N1 T1 is equal to P2 V2. The last thing to take over to the other side of the equation is V2. So it's multiplied here, I need to divide it, and therefore I'll rearrange the equation. So I'll just put this in a box here. So now I've got P2 equals P1 V1 N2 T2 divided by V2, right? So V2 here, N1 T1. I didn't actually write anything out here, I do apologise for that, so that should be like that, and they cancel out. Okay. I've also written the P2 on the left-hand side of the equation because we usually write what we're trying to find on the left. So I just flipped it around whilst doing that. That's the rearranged equation. Now it comes to the stage where you need to put some values into the equation. The values in this question were given to us as if you're not familiar with Kelvins, that doesn't really matter. It's just a unit of temperature that we need to use here because it's one of the gas laws. Alright, so we're going to substitute all of those values in here. So 610, I'm not going to convert this prefix here. I just need to acknowledge the fact that by using a pressure here in kilopascals, my answer will already come out in kilopascals. You could convert to pascals and then back again, but there's no need to. 160,000 multiplied by N2, which is 62 times 10 to the 6, and T2, 294. 171,000 on the bottom for V2, times by 55 times 10 to the 6, which is N1, and T1 is 292. So a lot of numbers to put in there. That's the substitution completed. Now here's a little trick. This is 160,000, this is 171,000. You can simplify that to make it easier to put the values into the calculator and faster and less, so therefore you're less likely to make a mistake, by appreciating that 160,000 is equal to 16 times 10,000, right? And 171,000 is 17.1 times 10,000. Okay? So if you've got 160,000 over 171,000, that's exactly the same as 16 divided by 17.1, because you've got 10,000 divided by 10,000, and just as we've been seeing, x divided by x is 1, or any number divided by itself is equal to 1. So this is exactly the same as that times 1. So 16 divided by 17.1 is a much easier set of numbers to put into your calculator. What it actually means for typing this long calculation into your calculator, and I'll just say as well, it's always a good idea to put that bottom, you should put that bottom bit in brackets, so that when you're putting it into your calculator, you divide by all of that rather than just this one. So when you're putting it into here, you can just write 16 here, and this can be 17.1. Okay? So that makes it less likely that you'll make a mistake, because you don't have to make sure you've got the right number of zeros. And when my students have been doing these calculations, some of the students who haven't done that have made mistakes and got power of 10 errors because they've got the wrong number of zeros in their calculator. Related to that, you see we've got a times 10 to the 6th there and a times 10 to the 6th there. So 62 million divided by 55 million is exactly the same as 62 divided by 55. So you can cancel those out as well and just do 62 divided by 55. Okay, so that makes things a lot easier when you're putting it into your calculator. And when you get as in terms of your answer here is 648. As I mentioned before, I put my pressure straight in kilopascals, so it's going to come out in kilopascals. And that is a brief run through for rearranging, and hopefully you understand why things move to the other side of the equation a little bit better than you did before you watched this video. Hope it was a help.